Okay, so today we're going to do homework 4, second angle, my phone. And for this homework, part A, derive Brodian's Jacobian update by the argument that updated Jacobian should have the same result as the original Jacobian on vectors perpendicular to the change in the independent variables. Okay. Okay, so we're going to start at the beginning, and what we're going to do is draw a diagram. Going to make it better to kind of represent what we're going to talk about. Let's put like some random function, right? Who cares? Put a point, 2 points on, and then have the x and the y, but for y instead, we're going to use f of x. Oops. For a function, and x, of course. And then we have x. We're going to use the variable k, and then x k plus 1 because, we're going further down. And then we have f of k and then f of k plus 1. And so for this, what we want to do, we're essentially with this Jacobian and everything else, we're going to be finding kind of the slope of this, usually rate of change and whatnot. And so typically when you find the slope of a linear line with 2 points, you use the point slope formula. Okay, so our slope is also the derivative. So we're going to have df over dx, and this is equal to y2 minus y1 over x2 minus x1. So you're going to have fk plus 1 minus fk, and then underneath that in the denominator, you're going to have xk plus 1 minus xk. And this is going to be our point slope formula. We'll be talking about the Jacobian, and the Jacobian is the derivative of the vector field with respect to each independent variable. And so what we're going to do actually is have Jacobian k is equal to that thing that we did up there. Okay, so then next with this formula that I put right there, we're going to move things around to get fk plus 1 by itself. And so how we're going to do that is going to multiply the xk plus 1 minus xk onto the jk, right? And so you're going to have fk plus 1 minus fk is equal to, and then we're going to move that to the other side. So jk is times xk plus 1 minus xk. And so with this, you just add fk to the other side, and you will get f. Ooh, I can't believe I wrote fx instead of fk, but it's okay. It basically looks the same. Fk plus 1 is equal to jk xk plus 1 minus xk. And we make sure that that's here. There we go. And so ultimately, what we want to do is we want to have xk plus 1 equal to a value that makes our function fk plus 1 equal to 0. And so let's rewrite this as 0 is equal to jk xk plus 1 minus xk. And how did I forget to add my fk up there? Let's see, plus fk plus fk. Okay, so we got that. But then there's also going to be instances where the function is not quite equal to 0. So this is going to be our first equation, and our second equation is still going to be just the fk plus 1 is equal to jk xk plus 1 minus xk, and then plus fk, of course. And it's going to be our second function. Okay, so since xk plus 1 minus xk is a common theme with all of our functions, we're actually going to set that equal to something. So we're going to have d denote, something happened. Okay, d equal to xk plus 1 minus xk. That way we don't have to keep writing it all over again. But what we want to do is find the difference between equation 1 and equation 2. So we're going to take equation 1 from equation 2. And so what we're going to do is fk minus 0. Of course, it's just going to be fk plus 1, or fk plus 1 minus 0 is going to be fk plus 1. And so, give me a second. Wait a second. I think I did something wrong. I think it's the jk. I forgot that it's not jk, it's jk plus 1. And so we're going to have jk plus 1 minus the jk, since they're two different ones. That's why it was wrong before. You can't have it cancel out. So you have jk plus 1 minus jk. And of course, your fk's cancel out. And then this is going to be multiplied by our variable d. This is multiplied, but we will talk about the dot products soon. But, okay, I'm not muted. What I do want to go over is the thing about vectors and being perpendicular. And so what we're going to do is we're going to have v dot product d is equal to 0. This denotes that they are perpendicular. Their vectors are not adding to each other or contributing to another vector. And so since that's true, we also have v product d transpose is equal to 0. And then also v transpose dot product d is equal to 0. And these are all going to be related back to our own formula. And so with this, what we're going to do is we're going to have our jk value, jk plus 1 transpose v is equal to the same thing that jk, or not transpose, but dot product v is equal to the same thing. Okay. And then also a little bit of fun workaround, and you get that jk plus 1 minus jk dot product b is equal to 0. And then also with this, you're going to get, or since we had our one variable d earlier, it's actually jk plus 1 minus jk dot d is equal to fk plus 1. Okay, and so with this, we're going to take from the top the v times d transpose is equal to 0, and we're going to say that, here, we're going to say that jk plus 1 minus jk is equal to d transpose. Okay, so next we're going to set this up times d. Okay, so we're going to set this up as jk plus 1 minus jk, and then you're going to have fk plus 1 d transpose plus 1 minus jk is equal to fk plus 1 times d transpose. And then on the bottom, we're going to have d times d transpose, right? And so our d is equal to what was up here, xk plus 1 minus xk. And then with this, what d is our change in x. So that means that we'll write this as d is equal to delta x. And so what we get is actually d transpose is equal to double. Why is my mind blinking right now? That's actually really funny. No, it's okay. We're just going through it right now. So that means that we're just doing absolute value. That's what it is. Might be slightly dehydrated. It's okay. Okay, so change in x. That's great. Okay. Oh, good God. Right? Yeah. Okay. So then what we're going to do is we're going to kind of rewrite some stuff. So to get jk plus 1 by itself, right, the Jacobian, we're going to say jk, just kidding, plus, and then fk plus 1, and This is times the D transpose and then the D transpose. All right, and then our D transpose is actually that change in X. So we're actually just going to write this as Fk plus 1 is equal to J. Why did I say Fk? Jk plus 1 plus Fk plus 1 times that product. Change in X transpose over, and then what do we have up here? This one is equal to squared. I don't think I need the double absolute value signs, but almost done. This is going to be our main focus here. And then also what we want to do is talk about that change in Fk is equal to Fk plus 1 minus Fk. So then you also get Fk plus 1 minus Fk minus Jacobian times change in X. And then finally, just for funsies, honestly, Fk plus 1 minus, and then in parentheses, Fk plus Jk change in X, right? Because the minus sign's on the outside. We're just going to say that this goes to 0 to make this true, right? And that should be everything for part A, where we derive the Brodian's Jacobian update via the argument that the updated Jacobian should have the same result as the original Jacobian on vectors perpendicular to the changed independent variables. Thank you. Good night.